So I want to talk about some vanishing results for completed cohomology. So I guess you will hear more this week. So this is joint work in progress with Kaiwen Lan. Yeah, so first I want to spend some time to talk about motivation. So why do I care about what type of vanishing results we want to show? So so instead of talking about the vanishing results for rational for completed cohomology, I will first recall some known results for cohomology of Shimura varieties. So let me just discuss the example in the simplest case, but already it sort of tells you a lot of things. Just in the case of modular curve. Okay. So let gamma be a congruent subgroup SL2Z. So we will assume it's sufficiently small so that the quotient of the upper half plane. So this denotes the upper half plane. The quotient by gamma it's really a manifold. So this is a Riemann surface. So this is the usual modular curve of say with level gamma. And we can consider its cohomology with coefficients indexed by a non-negative integer k. So given k, we can consider so gamma is a subgroup of SL2Q, so which has a standard representation on the two-dimensional vector space. So this is standard representation, and we can consider this case symmetric power. This defines a local system. Let me denote by VK on my modular curve. So it is known that so it's well known, but let me probably just write as a theorem that if k is at least 1, well, in this case it just means k is not 0, then well, this is an open curve, so it only has h0 and h1. So h0 of vk is equal to 0. Okay. So this is some type of vanishing result. So in some sense, the cohomology will only be concentrated in middle degree when k is not 0. And for general k, well, it really just means that now I allow k equal to 0. So so certain Hausdorff weights are missing in H0. It's better to write H less than 1, where 1, you should really regard 1 as the middle degree. Okay, I will be a little bit more precise about this statement, but the idea is that even though H0 can be non-zero, but I want to, in some sense, there is still some vanishing in terms of Hausdorff weight. So the cohomology class appearing H0 is more singular. Okay. So how to actually prove this? So I shall prove. So we will like y bar to be the compactification of y, and on y bar there's a usual automorphic line bundle. And the only thing we need to know about this line bundle is that actually it's positive. Okay. And now to prove this vanishing theorem, so we need some way to express this singular cohomology in terms of things more related to this omega. So this is the well-known as Shimura isomorphism. Which says that so if you complexify your local system, which tend to see, so it means a natural decomposition into hi bar of omega to minus k and hi minus 1 y bar omega k plus 2. Sure. So we see that now if we just look at the H0, so the right hand side is just y bar omega to minus k, and the direct sum with h minus 1 omega to k plus 1. But so this sheaf omega k plus 2, of course, there is no h minus 1. And for this term h0, so 1k is greater than or equal to 1 because the degree of omega is positive. So we see that the degree omega to minus k is negative, which implies that there is no h0. So that's actually how you prove this vanishing result in this simplest case. Okay. So let me summarize like things used actually in this proof. So so of course, first the starting point is this isomorphism. So one way sort of to think about this is it's really coming from Hodge theory. And this is really some kind of a Hodge decomposition. So yeah, sorry, I should write it here. So so one main ingredient is the Hodge theory, and in fact, so using Hodge theory, I mean, first we use in some sense Riemann-Hilbert to relate singular cohomology with cohomology of vector bundles with flat connections. So relate to coherent cohomology. And second is that the Hodge theory actually tells you that these kind of coherent cohomology, the way they show up, they contribute to the singular cohomology is why some direct sum. So there's some direct sum decomposition on the right hand side, and the one way sort of to think about this is that actually on this singular cohomology is there's an action of this Deligne torus, so which gives you this decomposition. So So another way to think about this is that there's some the symmetry for this cohomology group. So coming from Hodge theory, so as I mentioned, so sort of one way to think about this is that there's the Lane torus acting here. So this is for this decomposition. The second step is that well, now you write everything in terms of coherent cohomology. You need to have some vanishing results for coherent cohomology. And here, what we use is that we're saying, well, if we add some line bundle, which is anti-ample, so which means there's an active of an ample line bundle, then it has no H0. So for higher dimensional varieties, what you are asking for is a vanishing not just for H0, but vanishing below middle degree. And this type of, and also the positivity of a line bundle is generalized to the, I mean, in general, you're just looking at the ample line bundle, and this kind of vanishing results is exactly what is known as the Kodaira vanishing. Or Kodaira type of vanishing result. So I will just highlight these sort of ingredients used in the proof. So as I mentioned, so for H0, when k is equal to 0, even though you have H0, so k is equal to 0, this is just looking at connected components. Of course, you have H0, but still what you see is that actually, so let me write it here. Is that for H0, so I will just look at C coefficients. In this case, the actual Shimura isomorphism is just isomorphic to y bar O H minus 1 omega 2, which we know is 0. But actually, as I mentioned, so you should think that so there's an action of the Lane torus. So actually, each term carries a Hodge-tape weight. So the Hodge-tape weight here is 0. And this term actually has the Hodge-tape with 0, 1. So in some sense, it means that for a Hodge-tape with 1 term, actually is missing in H0. So even though H0 not vanished, but actually some component, certain weight part vanishes. So this is also some general phenomenon for cohomology below middle degree. And I want to remark that actually this is sometimes will be enough for applications. For example, if you're interested in, I forgot to say, but I think everyone here in the audience knows that modular curve is defined over a number of fields. Or if you use p-adic, well, this is a p-adic talk, so let me use p-adic coefficient. So everything, all the cohomology groups, that carries an action of the absolute Galois group of this number field. So this, because there is certain Hodge-tape weights missing in the below middle degree, then you can use this kind of result to show that, well, if you if you have a Galois representation which has enough Hodge-tape weights, then it cannot appear in the cohomology below middle degree. Yeah, so I just want to mention sort of one sort of possible application of this kind of result. Of course, in this case, is that this is probably a very bad example because, well, in this case, I only have H0, and because I'm looking at connected modular curves, so the Galois action is trivial. But the type of this type of argument works quite general. So this is the result for modular curve, but actually the pattern, we have the same pattern for general Shimura varieties. Let me just briefly mention what is true also for general Shimura varieties. So for general Shimura varieties, So let Gx be a Shimura datum. So here G is a reductive group over Q. And let's say we have a level this is a neat open complex subgroup of G finite adel. Then we can form the usual Shimura variety with level of level K, which is just a double quotient X times G finite adel. Okay, and the GQ. And recall that in the case of modular curve, so we need to, I mean, the local systems so we are interested in are indexed by non-negative integers. So that's because we were in the case of SL2 and the dominant weights are indexed by non-negative integers. So in general, for general Shimura varieties, I mean, you need to choose a dominant weight of GC. So when base change G to C, which defines a local system. V mu on my Shimura variety. Then, well, sorry, just one more notation. So throughout this talk, I will always use D to denote the dimension of my Shimura variety, which is also the dimension of X. Yeah. Then the cohomology of this maybe let me state it in this way. So the theorem of Lee and Shimura says that well, if mu is regular, then the cohomology. Oh, sorry. Of this local system vanishes below middle degree. So well, in the case of SL2, so I mean the weight it's a single. Sorry, it's irregular if and only if K is equal to 0. So this is exactly what generalize the condition K is not equal to 0. And you also mentioned that the method is based on automorphic representation. So actually, their results hold not just for Shimura varieties, but also for local for more general local symmetric spaces. But the input is still using automorphic representation. But if you remember, so the proof, the sketch of proof I gave for modular curve actually doesn't use any input from automorphic representation. It's really just some consequences from algebraic geometry. So if you're interested in results, just prove that purely by some algebraic geometry method. So there's a very nice result by Kevin Lan and Sue. The result is slightly weaker in the sense that it says that its mu is sufficiently regular. I will explain what it is in a minute. Yeah, then we have the same sort of vanishing. So think in their paper they have a due here. Let me just follow their convention. So sufficient regular, as the name suggests, so it's a stronger condition on being regular. Sure, but actually it's not that different from regular. So it's equivalent to being regular if we are not in of G. Each factor of G is not of type, or non-compact factors. It's not of type B and C. So, well, for type BC, you need to require something slightly stronger. So usually for regular just means that if you pair your weight with any co-root, it cannot be 0. Here you require that when you pair with any co-root, it cannot be not only 0 but also a plus and a minus 1. So you see that the result is a slightly weaker, but one good thing is that actually their results they can also they also have vanishing results for coherent cohomology. So as I mentioned, so already in the case of modular curve, you look at H0, so we see that there's still some component missing, some Hausdorff weights missing there. So they also have similar results in this aspect, and their method is more geometric. Sure. So let me just say their method is more geometric and actually relies on vanishing results. Kodaira type of vanishing results from mixed Hodge module, a series of mixed Hodge modules, and sort of this kind of I mean, this result of Lan Su is what we're going to try to generalize to the setup of completed cohomology in today's talk. Maybe now I'm going to define completed cohomology, but before that, are there any questions so far? Okay. Sure. Now let me try to state the main result. So as I mentioned, so it will be a very similar result to this theorem, but for completed cohomology. So, well, first I need to tell you what is completed cohomology. So this was introduced by Emerton. So to define completed cohomology, you need to fix some level. Well, sure. Yeah, I should say throughout this talk. So we fix a prime p, prime number p. So if you fix a level away from p, then so to get the Shimura, to define Shimura variety, so we need also a level at p. So let Kp be an open compact subgroup of GQP. Then we can look at the Shimura variety at this level. Distortion coefficient sigma p to the n. So instead of like usual for p-adic cohomology, we take the inverse limit of n. So the insight of Emerton is that the first you take the direct limit over all the level at p, then you take the inverse limit. So in some sense, you interchange the process of taking these two limits, and somehow, as a result, what you get, this is let me denote it by h tilde I. This is called Emerton's so completed cohomology, or p-adically completed cohomology. It's much larger than the usual cohomology of Shimura varieties. So in some sense, it comes from an interpolation of a cohomology of Shimura varieties on the finite level. So I mean, it's clear from the construction. It requires some a bit more work. So what you can show is that this is p-adically complete. And also carries an action of GQP, and this action actually is admissible in some sense, which means that there's some finiteness property for this action. And I forgot to say so, but let me say it here. So all the Shimura varieties can be defined over some number field, some reflex field. L, which means that the completed cohomology also carries an action of the absolute Galois group of L, and we expect that in the middle degree, so this Galois action, if you look at this Galois action, it actually has a lot of very interesting sub Galois representations. So we expect so H2 to D contains many Galois representations. So I mean, I'm not going to make precise what I mean by many here, but just if you're familiar with Emerton's work on Fontaine-Mazur conjecture, I mean, one of the starting points is that for Emerton is that if you have some Galois representation, you try to first show that this Galois representation will appear in this completed cohomology. So in some sense, it's very large. So so this is for the middle degree, and what we do, and for below middle degree, maybe let me say Galois representations. Are more non-generic. So, for example, I mean, this the precise one possible precise meaning of this generic is in the work of Cariani-Schulze. So I guess you will hear more about this later in this week in Haman's talk. So this means that so compared with the cohomology appear in the middle degree, so we sort of expected that the cohomology class appearing below middle degree are more singular. So if you input some generic assumptions, so you shouldn't see any of them. So I should say, so yeah. So in their work, in the work of Cariani-Schulze, so this kind of generic assumption, they put this kind of condition using the action of Heck operation. So they use information in some sense away from P. So in this talk, so we also want to prove some concentration, we want to Q the cohomology below middle degree, but instead we just want to use the action, the information at P. So far, I only talk about the cohomology below or equal to the middle degree. I mean, there's a reason for me to do this. So as I mentioned in the title of my talk, so I will only interested in the rational completed cohomology. So I will later invert P. So I will not care about the torsion here, although the torsion of completed cohomology also carries a lot of information, but yeah, so in this talk, we will only study rational classes. So if you're just interested in the rational classes, so there's a very nice result of Juan Esteban Rodriguez Camargo. It shows that actually, if you invert p, this is equal to 0 above the middle degree. So in some sense, we can only just concentrate on the degree up to d. Okay, so as I mentioned, so we want to input some generic assumption, and it's already clear from the results I mentioned for Shimura varieties. So the generic assumption really comes from you input some condition on the weight, but weight really comes from the action of Lie algebra. So first we need, as I mentioned that so the group acts on completed cohomology, but the Lie algebra does not act on it. So first thing what we need to do is that we take the subspace of a locally analytic vector. So here CP is the p-adic complex number. So let me base change to CP and take the subspace of a GQP locally analytic vectors. So it's really the subspace of vectors on which locally on GP the action is given by some convergent power series. So at first you might wonder how large this subspace is. It's a very nice result of Schneider and Tetzelbaum. Tells you that actually this is really a dense subspace. So actually you don't lose that much information in certain sense. So once on this locally analytic vectors, so because the action of group becomes analytic in some neighborhood of the identity element, and now you can take the derivative and consider the Lie algebra action. So it carries an action of the Lie algebra. So now I can state the main theorem. So let lambda be a character of ZG. So ZG here denotes the center of the universal enveloping algebra of G. Just be a character. So let me emphasize here that so because we are on the infinite level, so this weight doesn't have to be integral. So not necessarily integral. So, and suppose lambda is sufficiently regular. So I will explain these terms in more detail later, or give you some examples of what this means. Then we have that if you look at the if you look at the locally analytic vectors of this completed cohomology, and if you look at the lambda isotypic part, it's actually equal to 0. So here this means lambda isotypic part. So I mean, just that means see, it should be clear what it means. And here the sufficient regular again, means that if you pair your infinitesimal character view as a weight and pair with co-root, you cannot take certain values that are very explicitly determined in each case. So any lambda prime and in the orbits of lambda, so this is a Bell group orbits of lambda in the weight space. Well, let me say this is the usual action, not the dot action. So which means that the usual action, not dot action. So which means that everything, for me, everything, all the weight has already been shifted by rho. Okay, so and then for any co-roots, so again, the pairing cannot take certain values. So yeah, so instead of really just writing down explicitly what it is in each case, so let me just mention, just give you some idea, just in the following two cases. Sure. So let's say for type A, let's say G is just isomorphy. Let's say it's just isomorphy to GLN. Then for this lambda, this class, this orbit is the same as given n numbers and ordered. So you see, I already shift by lambda. Sorry, we shift by rho. And so then lambda is sufficiently regular. Simply means that AI minus HA is not equal to plus or minus 1. Yeah, so because if I do not shift by rho, for dominant weight, it's exactly the same as the condition of being regular. Okay. So this is for type A, and for type C, so in this case, so lambda is again well gives you n numbers and you can permutate it and change by the sign for each AI, and sufficient regular just means that so when you pair with co-rooter, so you have AI plus minus HA is not certain. Guessing in this case, it's not plus minus 1 plus minus 2. And for each AI, it's not a plus minus 1. Yeah. So this is so I hope that these two examples give you some idea what this main result says. Yeah. So this is a statement of a main theorem. So let me make one remark and take questions. So remark is that a more refined version for missing Hausdorff weights. Well, I guess here the weights might not be integer, so Hausdorff send with in H2 to when it's below middle degree is in progress. So actually we have we know we have some strategy, but more or less we haven't really work out all the details. But I just want to mention that we also can say, well, for general weights, if we do not impose this sufficient regular condition. So we know, so it can happen that we do have cohomology below middle degree, but we still have the same phenomenon that you won't see all the hot state weights, and even what we would like to see is that given a hot state weights and a priori you will have a vanishing range for this hot state weights. Yeah, so this is a statement of the result. So in the last 20 minutes, I want to sketch a proof, or maybe just highlight some ingredients using the proof. But maybe before that, are there any questions for the statement of the result? Sorry, I couldn't quite hear. Can you repeat?
How essential is it here to base extend everything to CP? Would the result be true over a smaller subfield?
Yeah. It is true. If you just do not tensor with CP and assume the weights take value in QP, then you also it is also true. Yeah, actually, you can deduce that result from this result.
Thanks.
Yeah. Thanks for the question. Are there any other questions? Okay, so let me just give a quick sketch. Strategy. I don't. So if you remember, so I mentioned at the very beginning that if you're so even already in the case of modular curve, so we need the ingredients. So if you remember, so first we need to translate the problem of so as you see, so completed cohomology is really built out of singular cohomology. But if you remember, so on the modular curve, so what we first do is that we write it in terms of a coherent cohomology. So we need a similar thing here, and actually this was done by Schultz's primitive comparison. So which allows you to write your singular cohomology, your état cohomology, as some kind of which looks like some kind of coherent cohomology. I will be more precise later. Now, if you for the second ingredient, if you remember, so in Hot theory, we have Hodge decomposition, which really comes from the symmetry of the which comes from the action of the Deligne torus. So there's some hidden symmetry there. So now again on the completed cohomology, there is also some hidden symmetry. But actually, it's not clear just from the definition. So some hidden symmetry of these locally analytic vectors. So roughly speaking, so there's an action of ZM on it. So where M is a subgroup of G, so it's the levy of a parabolic. So this is determined by a levy determined by the Hodge cocharacter. And M is a levy, and and ZM denotes. So ZM denotes the center of the universal envelope algebra of M. So we know that on this H theta I, so the Lie algebra of G acts on it. So in particular, ZG acts on it. So the point is of this ZM, there's a natural action of ZM which extends the action of ZG, And second is that actually commutes with G. Which is not I guess in the case of modular curve, sort of one way to think about this action, why you should believe there's such extended action is that on this completed cohomology, so if you remember at base change to CP, so you have a Galois action and you have the sin operator. So if you incorporate the sin operator act on it, you will get this extended action. But in general, the action of sin operator is not enough. So what you really need to get this action, to unlock this action, is it really comes from a geometric sin theory. On Shimura varieties. So in the case of modular curve, this was done by my previous work, and in general for general Shimura varieties, this was done by again in Rodriguez' thesis work. Yeah, so this is one important ingredient in the proof. And if you remember, those lost all the sort of vanish result. We need some vanish result for coherent cohomology, and this sort of the most powerful one is the Kodaira type vanishing. So we also need some Kodaira vanishing results in this context. But so this is in some sense in some mixed characteristic cases, and it's well known that I mean even for in characteristic P variety, so Kodaira vanishing can fail. But fortunately, so yeah, very recent work of Bhatt. So he provides such a Kodaira type vanishing result, which will be enough for our work. Yeah, so I would say a bit more about this probably this, and briefly explain what sort of why this will help. So let's see, I still have some 10 more minutes. So okay, let me start. So let me first say what is primitive comparison, or what I mean by primitive comparison. Yeah, so yeah, just for simplicity, so let me just assume that the Shimura variety we are interested in is compact. Okay, so in general, if it's not compact, you work with toroidal compactification. Let me ignore this here, but you can do that. And also, let me also assume this is of Hodge type. It's not really because the proof I'm going to explain only works in Hodge type, but it's simply because that some geometric construction I'm going to do works well in the Hodge type case, and in general, if you just interpret everything on some derived level, it still works. But let me just assume for simplicity, we are not in that general setup. Yeah, so let me fix isomorphism between this p-adic complex number and the usual complex number, and let me use this to denote this is the rigid analytic variety or adic space associated to the Shimura varieties. So rigid analytic variety. And now you can consider the inverse limit when you vary the level at P. Well, in general, it just exists as a diamond, but if it's Hodge type, so it's just a perfectoid space. Generally, if it's not Hodge type, you just regard it as a diamond. So the primitive comparison just tells you that so the completed cohomology, when you take completed tensor product with CP, it's naturally isomorphic to the coherent cohomology on this infinite level Shimura variety. Or I should say this is a corollary of this primitive comparison. Yeah, so this is the first ingredient. So now I want to mention what I mean by Kodaira vanishing in this case, because this is not some finite type of variety. So let me explain a very beautiful result of a Bhatt. So this is 1. This corresponds to 3. So let Z be a proper. Well, let me just state a very special case, which is enough for our purpose. Proper Fly scheme over OCP, and let me assume its generic fiber is smooth. Actually, this can be weakened. And let's say L is an ample line bundle on Z, and let OZ perf be this so-called perfectoidization of OZ. So this notion was introduced in the work of Bhatt and Schoser on prismatic cohomology. So really, in the world of direct, the direct categories on the on this. So this is the formal scheme, the p-adic completion of Z. So formal scheme associated to Z. And with this setup, then you have almost Kodaira vanishing. So it's below the dimension of Z, or the relative of dimension of Z. So dimension of the special fiber. You have OZ perfed mod P to the n tensor L inverse is almost 0. Yeah. So roughly speaking, this result says that well, in general, so we know that Kodaira vanishing fails in general for a mixed characteristic, but this result of Bhatt says that well, if you allow yourself in the almost world, and if you're using the correct structure sheaf, in some sense, if you're not using the original structure sheaf but using this perfectoidized one, then you still have this Kodaira vanishing, so this result will be enough for our purpose. So you can imagine that in our case, we will take Z to be finite level Shimura variety. We take some formal model, and yeah. So let me say how to use that. Sorry, it will slightly abuse of notation. So L will be some ample line bundle. So it will be some automorphic ample line bundle. On my finite level Shimura variety. So actually, there are a lot of choices. So if you start with one, you can take its power. So in practice, we will take the minimal one, the one as minimal as possible. And then, so we have this infinite level Shimura variety, which projects onto finite level 1. Let me call this map pi kp. So then one corollary of Bhatt's result says that, well, hi of the pullback of this ample line bundle, and its inverse is equal to 0 when I is below the middle degree. Okay. So we see that Kodaira vanishing tells you that we have the vanishing for below middle degree after tensoring with some ample line bundle. Oh, sorry, inverse of an ample line bundle. Okay. But if you remember, so what we're interested is not this untwisted version. So this is what is isomorphic to the completed cohomology. So somehow we need an argument from this twisted version to this untwisted one. So actually, so people already knew how to do this in the context of localization. So this is you should call translation functor. So I guess I will not have time to really explain the detail in this context, but let me try to explain the idea here. The idea is that so yeah, sorry, I forgot to mention one ingredient. Is that so we have this Hausdorff period map. We have the flat variety defined by the parabolic defined from the Hausdorff character, and we have the Hausdorff period morphism from the infinite level Shimura variety to this flat variety. And because in one property for this Hausdorff period map is that this is GQP equivalent, and moreover, our ample line bundle, because we choose it to be automorphic, we assume to be isomorphic. Actually, it's isomorphic to pullback of some line bundle on the flat variety. So it's up to take twist for some ample line bundle LHT on the flat variety. So in some sense, the geometry is all described by the flat variety. So what we are going to do is that so choose V, which is a finite dimensional representation of the Lie algebra G, such that there is a surjective map when you tensor V with the structures of the flat variety. So there's some constant vector bundle. It has a so there exists a surjective homomorphism from this to this line bundle. So as a vector bundle. So as a vector bundle, and this is G equivalent. Another way to say this is that we require, if you look at the representation of V as the Lie algebra of P, so it means a surjective map to lambda m, which is this is the one-dimensional representation correspond to Hausdorff. So this line bundle Hausdorff. So this line bundle on the flat variety just is the same as a character of your Levy. So it's the same. So we choose this. So then we have when we twist by our Hausdorff, so inverse of it. So we get the sequence of a vector bundle on the flat variety. So now what we do is that we use Hausdorff period map to pull back this this sequence and take locally analytic vectors. And then, if you remember, so I mentioned that. Sorry, I'm a bit over time, so I will just finish in 1 minute. So So actually, using geometric sense theory, so everything is equipped with an action of Zm. So you use Zm. In some sense, you fix some lambda isotypic component on the level of sheaves, and then you consider the infinitesimal action of G, and somehow because the infinitesimal character of this guy after you do this will be different from this guy, so we will get a splitting of this sequence in the category of derived category of abelian sheaves. So not as vector bundles, but as a direct in the direct category of abelian groups, sheaves of abelian groups, because they have different infinitesimal character. And so that's how we pass from the vanishing result for L inverse to the structure sheaf. And this condition, sufficient regular, really guarantees that these two will have different infinitesimal characters. Yeah, sorry, I'm already out of time, so let me just stop here. Yeah.
Thank you.
Yeah.
All right, thanks a lot for a very nice talk. Are there questions?
Hi, so I have the question. So in the case where you don't know that the Shimura variety at infinity level is perfectoid, how do you use the primitive comparison theorem?
I mean, it still holds. I mean, the primitive comparison really is just you know it on the finite level, and you take the direct limit over all the levels. Maybe you are asking why this is true. But I mean, if you interpret this cohomology grouping in the correct sense, then it is still correct.
So at the last step, you related the cohomology of V tensor L to O. Then how do you control the cohomology of F, the kernel?
You don't need to control it. The point is that these two have a different infinitesimal character, so this will split. This sequence splits. So the vanishing in the middle term will imply the vanishing for this term. So you don't need to know anything about F. Sorry, does this answer your question?
Yes, I think so, yes.
Okay. Yeah. Maybe I should say that to get more refined results, one is not sufficient regular, which means that these two have the same infinitesimal character. Then you have to understand this F. Yeah, that's what I mentioned. Is some work in progress. Yeah, but if you just in the sufficient regular case, then yeah, you don't need to know anything about F. Once you calculate these infinitesimal characters.
Would you expect that sufficient regularity could be sharpened to just regularity, or?
Actually, I don't know. Yeah, actually, I'm lying also a little bit that this sufficient regularity is slightly weaker than what Lan and Su's work. So already in their work, that it seems this is the limit of using this kind of Kodaira type vanishing results. So I'm not sure whether it can. Yeah, I don't know. Yeah, that's a very nice question. Yeah.
Can you explain again this? I think you mentioned at the end with the splitting at the end that it's not as vector bundles.
Yeah. Yeah. Maybe just let me just give one quick example. The most well-known example is if you look at on P1, you have a non-splitting exact sequence as a vector bundle. So I have this non-exact non-split exact sequence of vector bundles, but when k is not equal to -1, so this is a split as a sheaf of abelian groups, and but non-split as vector bundles. And the reason is that so everything admits action of SL2. So you look at the Casimir operator. act on it. So it acts on this same 1/4 of k. Sorry, maybe it's, I think 1/4 of k squared minus 1/4. And this is something like k plus 2, something like that. So when k is not equal to -1, you see they have different eigenvalues. The Casimir xy different eigenvalues. So you know it splits as a sheaf of abelian groups. So this is exactly the same arguments we are using here.
Okay, thank you.
Any further questions? If not, then let's thank Lue Pan again.